Section 5.4, triple integrals. Your homework will be made up of problems of 181, 183, 191, 211, and 225. So to begin, in this section, we define the triple integral of a function of f of x comma y comma z of three variables over the rectangular solid box in space R3. Later in this section, we extend definition to more general regions of R3. To begin, let's begin with Theorem 5.9, Fubini's theorem for triple integrals. So all this is saying is that we're able to integrate for three different variables x, y, and z. Now, we can rearrange x, y, and z in any order you would like. There isn't a rule saying what order to work with. Work with whichever order would be easier. So really, there is 3 factorial ways to rearrange them. So you can arrange them 6 different ways. X, Y, Z, X, Z, Y, Z, Y, X, doesn't matter. It depends on which one seems maybe easiest for you to set up or which one is the easiest way to set up. For a rectangular box, the order of integration does not make any difference in the level of difficulty in computation. We computate triple integrals using Fubini's theorem. We allow the order of integration the same way we did for double integrals, that is, from the inside to outside. So this first one is just a general example of triple integrals. It's set up for us. And we see that it first has us working with x, right? So we're going to do that integral first. So we're taking the derivative in terms of x. So we're looking for our x's. We have an x here. That is a constant. So if we integrate x, we get x squared times a half. Plus, those are just like numbers. So we have x, y, z squared. And we integrate for x at 5 and at -1. So this one isn't so bad to do. If we integrate for 5, we get 25 over 2 since it's being squared, plus 5xy squared minus 1 squared is 1 over 2 plus -1 yz squared. And if you clean that up, we end up getting, you can combine these like terms and divide evenly. So we get 12 plus 6yz squared, since these are like terms. Right? And then we continue to integrate. So now you're in a position that you've seen before. So now we continue to integrate 12 plus 6yz squared dy dz. And our bounds are when y is 4, for our upper, our lower bound is y is 2, our upper bound is z is equal to 1, and z is equal to 0. And from there, you continue with double integration as you did before. All right, we have another example. Oh, well, I'm sorry. I don't want to make this video too long, so the answer for that one should be, once you're done integrating with double integral, 36. So take a moment to pause the video and finish that problem. All right, so before we go into triple integrals, I want to make a quick note. So as you can see, you have many different ways to integrate. You have 6 different options. My advice is, if possible, get rid of z first, meaning do z first. And find your integral in terms of z for your upper and your lower. And then once you're done with z, you can let z be 0 and continue to work on the xy plane since you set z equal to 0. And that way you continue as usual. Depending on your question, you can continue using type 1 or a type 2 argument like we did in section 5.2, setting up our type 2 and type 1 arguments. Depending on the problem would let you know which one you think would be better, whether your function's already in terms of x or in terms of y, it would vary. Now, a disclaimer is not all integrals should start with the z integral. And that would vary on the problem, but I think a good plan is to try to get z out of the way first. But there is that condition that it might not be the easiest. All right, let's continue with our second example. Now, our second example is kind of also set up for us. Our question reads, evaluate the triple integral x squared yz dv, where where x is bounded by -2 and 1, y is bounded by 0 and 3, and z is bounded by 1 and 5. So we have a cube, and our bounds, just like the previous question, are also constants. So we can integrate at any order that you'd like, but I said z's first, right? So getting rid of z is nice. So our z is from 5 to 1, our y is from 3 to 0, and our x is from 1 to -2. And we're integrating the formula over the equation x squared yz, and you have to write them in the same order. So we have z first, so I have dz, then y, dy, and then x dx. And you continue to integrate just as you would any integral. We're just adding another integral to our argument. The answer for this question would be 162, and I'll let you finish it off. Now, integrating you know how to do. So what becomes the larger challenge in this section is setting up your bounds. And your bounds can vary depending on your function. And it just comes down to your best interpretation of how to read your image. So let's begin with theorem 5.10, triple integrals over a general region. The triple integral of a continuous function f of x comma yz over a general three-dimensional region in R3, where D is a projection of E onto an xy plane. So it says that we can write some function in dz and continue with the other two dimensions, x and y. Now here, it varies on your perspective. So figure 5.42, it shows the region of your bounded area for some z. And then you see here that it can vary whether you want to do type 1 because it's reading from your x-axis, or if you want to do type 2 because it's in, well, I guess in better words, it's in terms of your y coordinates or your y argument. So from there, it really varies on which one is, I guess a better word choice would be which equation would be easier to work with, right? If it's possible, it would be nice if we can avoid, for example, U substitution, because that kind of makes your integral more complex. So let's begin with the next example. Evaluate the triple integral of the function f of x, y, z equals 5x minus 3y over the solid tetrahedron bounded by the planes x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. All right, so one of my beginning hints for working with triple integrals, if possible, label your z bounds first. So set bounds for z. So we see that z is bounded by 0, the axis z equals 0, and this equation x plus y plus z equals 1. So let's set the equation equal to z. So I have z, and I move my other variables over. So I have 1 minus x minus y. And I see that the lowest bound is 0. All right, so we already set up our integral in terms of dz. So I have z is equal to 1 minus x minus y, and z is equal to 0. And we have our equation 5x minus 3y. Okay, but we're not done. We're still left to integrate in terms of x or y. Now from here, since we already set up z, next would be to make that variable that you set up first, in this case it's z, make that variable 0. So now let z equal 0 so that you can work with the xy plane. Since z is now 0, I'm now left with this beautiful xy plane. And actually, we have this right here. That's why I included this picture here. Now we're able to work with that xy plane. Now from here, it's up to your preference. Do you want to write a type 1 argument or a type 2 argument from section 5.2? So we see that everything is already in terms of x. So when I first saw this, I thought, okay, type 1 is the way to go. Because we see that this is in terms of x, so I can just read it goes from x is from 1 to 0, and then we have our terms of x. So I have y equals 1 minus x. So I chose, when I saw this, I thought type 1 would be a good one. So we see that our x bounds are from 1 to 0. Let me just write the integral. So my x are from 1 to 0, and then we get y, 1 minus x to 0, and we set up our z integral, which was z is 1 minus x minus y to 0. And of course, we're given that function, 5x minus 3y. And lastly, you want to make sure you line them up. So I have dz, and then I have y, dy, and then dx. And like I said, setting up your integral, I think, is the most challenging portion. I'll let you work this one out. Your answer, once you're done integrating, should be 1/2. Definition of area of a bounded region. Just as we did the double integral, the integral of 1 dA to find the area of a general bounded region D, we can use the triple integral of 1 dV to find the volume of a general solid bounded region E. The next example illustrates this method. So here we see that we have, well, the example reads, find the volume of the pyramid that has a square base in the xy plane of -1, 1, and -1, 1, and the vertex at the point 0, 0, 1, as shown in the following figure. All right, so reading this problem this first time around, I thought, okay, let's first set our argument in terms of z. So we see that z starts from 0 and extends all the way to 1. So I thought, awesome. I have z is equal from 1 to 0. And then I thought, okay, if that's the case, then I let z equal 0 and I'm left with the xy plane. But then I noticed the x plane goes from -1 to 1, and the y plane also goes from -1 to 1. So it kind of created a challenge to find the area of this one figure. So then I thought, let's go ahead and set up two different axes and let's read them separately. So we have these two axes to consider. So if we let y be 0 and we have z is always vertical, and x, we have this triangle right here. And we know these coordinates are all 1. Well, that makes it a bit easier to locate your values because we see that it's bounded between these equations. We have, well, y is 0, so we have x is equal to 1 minus z. No, that has a positive. That has a positive slope. So it would be x equals 1 plus z and x equals 1 minus z. All right, and then we also have the same triangular figure here with -1, 1, and 1, and that gives us, well, that's z and that's y. -y plus z equals 1, and y equals z equal to 1. I'm sorry, y plus z equals 1. Plus z equals 1. All right, so now we're here to consider, well, I'm actually have a lower bound that's an equation, and the upper bound is an equation, same for the other integral. A lower bound is an equation, upper bound is an equation. So it'd be easiest to let z be your constant because that stays strictly between 0 and 1. And something that I failed to mention in the beginning is that your last integral needs to be constants. So we set up our last integral, z from 1 to 0, and in this case, it would be best because our last integral needs to be a constant. Now we're left to choose for our bounds between x and y. So we see that for y, we have 1 minus z and 1 plus z. And for x, we have 1 minus z and 1 plus z. And we set up our integral. So we first have in terms of x, right? This is an x. Well, not in terms of x, but for x. And then y, and then z. And because we're trying to find the volume, we're integrating using 1. So this one was tricky. At first I thought, oh, this is not so bad, but I had to really think about how to break up these faces of a pyramid. Now with integration, we can also change the order. Now let's go ahead and read this introduction. With triple integral over a rectangular box, the order of integration does not change the level of difficulty of the calculation. However, with triple integral over a general bounded region, choosing an appropriate order of integration can simplify computation quite a bit. Sometimes making the change to polar coordinates can also be very helpful. So when I saw this problem, I saw a circle from this paraboloid, and I thought, okay, well, whenever I see a circle, my brain kind of thinks polar coordinates. But I saw the use of it once I started setting up a problem. So let me set you up the way these images try to set you up. So it seems like we have an argument in terms of x and y. So that leads me to believe that we should first try to write our bounds for z. All right, so let's first try our bounds for z. If that's the case, actually I'm going to write this in red because this is all not the best way. All right, so if that's the case, we need to solve for z. So let's go ahead and solve for z. If we do, we're left with, let's get z by itself. Let's move the x over. So I have 1 minus x squared, and we take the square root. So we need that plus or minus. So this is telling me that I'm going to let z be positive y minus x squared and negative y minus x squared. Well, using radicals is something that kind of is a turnoff because I know it might make my integration difficult. And it might even so make it more difficult because I have two variables under that radical. So I'm already not looking forward to integration. And then just with that, I think you should be thinking, well, maybe there might be an easier way. And of course there is. So now let me lead you through the correct way. So now, so this is correct. Ignore everything I said for the past minute. So now, notice that it is bounded or set with y equals. I'm talking about equations. You have y equals, right? So maybe it might be best to write your integral in terms of y first. And if we do, then we see that your equation is telling you that this is part of your question, that's also bounding it over the plane y equals 4. So your bounds for y are between 4 and your paraboloid, which is x squared plus y squared plus z squared. Okay, well, if we make our first integral y, then to continue forward, I can let y be 0, and continue to integrate in a plane without y. So this plane would be x and z. And if that's the case, if I work on the xz plane, then I need to find a point where they meet. Now I see that I have my arguments in terms of y, like we said. We have y equals x squared plus y squared, and I have y equals 4. So I can set the y's equal to each other to find that point of intersection. And we end up actually with a circle equation. We get 4 equals x squared plus y squared. And we did this to find a point where they meet. That's how we set our y's equal to each other. And when you see this, you should be thinking circle, right? Because we have x squared plus, I keep writing y, plus z squared equals 4. So that lets us know that we have a circle of radius 2. But you know, when you have circles, your brain should be thinking polar coordinates. And x squared plus plus z squared would be the same treatment as r squared, just like x plus y squared equals r squared. So this tells us that my r is 2, which we knew from just our circle image. And I can set up my last two remaining integrals in terms of polar coordinates. That's crazy. So you kind of start off with one integral, and then if it makes it easier, change to spherical. All right, so let me continue over here. So recall when you set up a spherical coordinate, or spherical integrals, it's always r dr d theta. So you have to set up your r argument first and then your theta argument second. So for r, we start from 0 to 2. So from 2 to 0. Our integrals, we start at 0 and we go all the way to 2 pi, a full revolution. So 2 pi to 0. Now we need to sandwich that. That's like your bread. And on the inside goes that first integral. So I first need to set up that integral that we set up for y. So let me try to write that in purple since I wrote that in purple. So I have my integral for y, which was y is from 4 to x plus x squared plus z squared, y equals. And my equation is x squared plus y squared, right? That's my first little integral. And then I proceed by setting my bounds that we just wrote for spherical. So that we have theta is from 2 pi to 0, and then r is from 2 to 0. And don't forget r dr d theta. All right, let's do that inner part first. So for that inner part, we can integrate, and we're integrating, oh, I forgot to write what we're integrating for. This is dy. dy. And I also wrote my equation incorrectly. We're integrating with the equation x squared plus z squared. So this is z squared. All right. Now we first integrate in terms of y. Luckily, y is not within our integral, so our integral is actually a constant. So if we integrate in terms of y, we just add the y and set up our bounds for 4 and x squared plus z squared. So no y, which is great because I don't have to worrying about the integral. So once we integrate, we're left with 4 minus x plus z squared times the square root of x squared plus z squared. So that's after we integrate and substitute those values in. All right, now we need to change to spherical. And that's really nice because remember, we're using that r squared is x squared plus z squared, right? So this is going to be r and that's going to be r, well, r squared. So that we're left with 4 minus r squared times the square root of r squared, which is just r. And don't forget to bring in that r from our r d theta. So inside our integral, I'm sorry for the mess, we should have, so this is just going to be r, and then r times r is r squared. So we're left with 4 minus r squared times another r squared, and then dr d theta, since we already counted that r from over here. So I'm left with r and then theta, which we already set up our bounds for. R is from 2 to 0, and theta is from 2 pi to 0. And then we can finish our integration. Now I'll let you finish this one, just like all these problems. You should get 128 pi over 5. Lastly, we have the average value of a function of 3 variables. Recall that if we found the average value of a function of 2 variables by evaluating the double integral over a region on a plane and then dividing by the area of the region, similarly, we can find the average value of a function in 3 variables by evaluating the triple integral over a solid region and then dividing by the volume of the solid. So very similar to section 5 point, I think we saw this in 5.2. Well, I think we saw this in both in polar and rectangular form. Your example reads, the temperature at a point xyz of a solid E bounded by the coordinate planes and the plane x plus y plus z equals 1 is T of x comma y comma z equals xy plus 8z plus 20 degrees Celsius. Find the average temperature over the solid. Okay, so we're working with this equation. Let's first set up our bounds for z so that we can set z equal to 0 and work with the xy plane. So solve for z. We have our equation here, and we have z is equal to 1 minus x minus y. So our bounds for z are 1 minus x minus y to 0. Okay, now to move forward, let z equal 0 so that we can continue to work on the xy plane. All right, by doing so, we're left with x plus y equals 1. And that came from our equation above. X plus y plus z equals 1. We let x be 0, so that we have x plus y plus 0 equals 1. So we have x plus y equals 1. So to find our intercepts, x is 1 and y is 1 from our equation given, and that bounds our area. Now that we set up our z integral, we can continue to set up either type 1 or type 2. So you want to choose type 1 or type 2. Remember, this is the equation. Well, it varies. It can be, this is x plus y equals 1. So it's your choice whether you want to make it in terms of y or in terms of z. I'm going to choose type 2. So this means I'm choosing my last integrals to be y. And we see that it goes from 0 to x equals 1 minus y. So let's set up our integral that we have so far. So we first set our bounds for z. So z is from 1 minus x minus y to 0. And then we have our setup for our remaining two parts. We have y is from 1 to 0. And then we have x is from 1 minus y to 0. Now we're integrating this over our equation, xy plus 8z plus 20. That's the function given. So then we write our integrals, our arguments, dz, then we have dx, and then we have dy. What we did here, this right here, is actually this part here. We're integrating over our function. Alright, this integral isn't too complex. It is time consuming, right? That's all it is, but you know how to substitute and integrate. So this is 147 over 40. I didn't look at the 7. 147 over 40. So that's the first part. Now we're left to find this other part. So for that, we use the same bounds of integration, but we do it over 1. So this v of e is made up of our same bounds for integration. So we have z is equal to 1 minus x minus y to 0. X is 1 minus y to 0. And y is from 1 to 0. But now it's over 1. dz, dx, dy. Your answer here is 1 over 6 once you're done integrating. But our VE is 1 over. So we have 1 over 6, which is just 6. Now we're left to multiply our answers. And this is the final part. So we're left with 6 times 147 over 40, which if we simplify is 441 over 20. All right, so that was 5.4 triple integrals. If I can give one quick summary, that would be that you can integrate in any order you want. You have 6 different orders of integration. So 6 different ways to set up your integrals. It might be the easiest way to get rid of z. So once you set up z, you're left to only work with the xy plane. Now once you have only the xy plane, you can choose whether you want to make a type 1 or a type 2 setup for the integrals. Whatever it may be, it is always best to let your last integral be in constants. So you want your last integral to be numbers. All right, that's it for section 5.3 5.4 triple integrals. Thanks.